Hello, Stat 300, and this is Professor Gonzalez, and I'd like to do some homework problems in the adaptive side of 1.5. Of course, this is symbolizing the adaptive side of ALEKS. Okay, so we have probability, and 5.1 is talking about some simple probability, but I do want to kind of go through some notes here to kind of get ourselves possibly up to speed for missing any details to this. So a probability experiment is one in which we do not know what any individual outcome will be, but we do know how a long series of repetitive outcomes would be. So an example. Okay, here it is. They're using the same example I just thought of. So for example, if we toss a fair coin, we do not know what the outcome of a single toss would be, but we do know what the outcome of a long series of tosses would be, about half heads and about half tails. So experimental probability is when you're actually doing a trial and maybe you toss a coin 1,000 times. That's experimental probability. Theoretical probability is when we just say, well, what's possible? Well, you can get a heads or you can get a tails. And when you flip a coin, you've got a chance of getting a head or tail. So what's the probability of getting a head? That would be 1 out of 2, or probability of getting tail, that's 1 out of 2. So the theoretic probability and the experimental probability, not necessarily the same thing, but we're going to find out the more you do, so if you flip a coin 10 times, it might not be half heads. But if you flipped a coin like 1,000,000 times, it would be really close to half heads. And that has to do with this law of large numbers, of doing the trial over and over again. The probability of an event is the proportion of times that the event occurs in a long run. So for a fair coin, that is one that is equally likely to come up heads as tails, the probability of heads is 1/2 of the probability. And the probability of tails is 1/2. Okay, so I already said that. So law of large numbers, there's that phrase I just said. Basically says that the probability says that as a probability experiment is repeated again and again, the proportion of times that a given event occurs will approach its probability. Okay, so saying pretty much the same thing. And that's what this graph is showing. Basically, it's showing on the very first toss, they end up getting heads, so it's 100% heads there. And then as they continued on after 5 tosses, here they are. And after 5 tosses, it's 6 out of 10 heads, or 60% of the time. And it kind of bounced around, and you could see after 100 tosses, what was it at? It was at 0.549 rather, so almost 50%. And then it dropped. It hit 1,000 but it dropped, but it's still, it's still pretty close to 50%. And then as we get closer, and then at 1,000 it starts coming up, and at 10,000, it's really honing in, and now it's going to stay tight to that line because it has all that history and basically the law of large numbers, the many trials that cause it to become close to our theoretical probability. And mathematicians, when they first realized this, it sounds weird now, but they were very excited, kind of like probabilities, like fortune telling, you could actually tell the future of something mathematically, but it felt very exciting as a new kind of math. Sample space, the collection of all possible outcomes of a probability event experiment, is called a sample space. Describe the sample space for each of the following. The toss of a coin. Well, the sample space is just what are the possible outcomes, heads or tails. The roll of a die, and we're assuming a 6-sided die. The sample space is 1, 2, 3, 4, 5, 6. Those are the possible outcomes. The selection of a student at random from a list of 10,000 at a large university. The sample space is all possible outcomes, which would be the 10,000 students. Probability model. We are often concerned with the occurrences that consist of several outcomes. For example, when rolling a die, we might be interested in the probability of rolling an odd number. Rolling an odd number corresponds to the collection of the outcomes 1, 3, 5, right? Because 1, 3, 5 are the odd numbers out of the sample space, which is 1, 2, 3, 4, 5, 6. In general, a collection of outcomes of a sample space is called an event. Okay, so the odd numbers 1, 2, 3, odd numbers 1, 3, 5 would be called an event. In the sample space is the total possible outcomes, which is 1, 2, 3, 4, 5, 6. Once we have a sample space, we need to specify a probability of each event. This is done with a probability model. We use the letter P to denote probabilities. For example, we denote the probabilities that a tossed coin lands heads by P of heads, and that would be the probability of heads. So the probability of heads, when we're talking about theoretic probability, of course, is there's one head on a coin, and then the total outcomes is head tails, so it's 1/2, or as a decimal 0.5 or 0.50. But now if it was not theoretic probability, if it was experimental probability, you would base it on the experiment of flipping a coin maybe 100 times, and then in that case it probably wouldn't be exactly 0.5. It'd probably be kind of close. And you can go off of this experiment. After 100 flips, they had 0.49. So it was pretty close. Okay, let's see, where am I at? In general, if A denotes an event, the probability of event A is denoted by the probability of event A, P of A. So here's some rules of probability. The probability of an event is always between 0 and 1. In other words, for an event A, the probability of event A occurring has to be greater than or equal to 0 or less than or equal to 1. Now, if the probability cannot occur at all, we call it the probability of event A is 0. It has no chance of occurring. And then the probability of A, if it is certain to occur, it's going to happen 100% of the time, the probability of A equals 1. And by the way, 1 written as a percent is 100%, right? So when you see 1, that's 100%. Okay. I think that's good. So let's move on. Let's see. Well, let me go back for a second here. Let's just use some red here. So if the probability of A was closer to 0, you can actually kind of think of this like a number line, maybe would be a visual. If I look at this and think of it as a number line, right, there's 0 and there's 1, and that's all we're looking at, from 1 to 0. And so the probability of flipping and getting heads is right here at 0.5, right? The probability of rolling a die and getting a 6, that's going to be down here somewhere. Probability of rolling a die and getting a 6 is going to be down there, which is like 1/6. Okay, and of course, if you wanted to say probability of flipping a coin and getting heads, you could say that as 1/2, right? You can write them as fractions or decimals. Often we like fractions in math because they're exact values. Converting fractions to decimals, often we'll have to reduce. But in statistics, often we do like that decimal, even if we have to round, that decimal converts to percents nicely and that kind of thing. So often it is a decimal or percent. Probabilities with equally likely outcomes. If a sample space has n equally likely outcomes and event A has k outcomes, then the probability of A equals the number of outcomes in A, which is called k, all divided by the number of outcomes in the sample space, which we call n. Now there's a reason why we use the variable n there. N also in our other problems had to do with sample size. So it kind of leaves the door open kind of to, or it kind of connects those two ideas to show that probability could be thought of when you're taking a sample of a population, right? There can be some probability going on there. And we'll talk about that in a little, probably in a page or two. But anyhow, once again, P of A, the probability of event A, and once again, if it had to do with probability of rolling a 3 on a 6-sided die, the number of outcomes in this event A, well, there's only one outcome because there's only one 3 on a 6-sided die, and then divided by the total number of outcomes in the sample space, there's 6 sides, so 6 possibilities on the die, so 1/6. All right, here's an example. It says, in Georgia, cash for lottery, a winning number between 0000 and 9999 is chosen at random, with all the possible numbers being equally likely. What is the probability that all 4 digits are the same? Now, what they mean by the same is repeating the same number. Okay, so remember, in order to do this, in order to do probability, you're going to need to know the number of outcomes in your event, right? The things you're looking for, and then it's going to be divided by the total sample space, which is the total number, or the sample space, which is the total number of outcomes. So let's see if we can figure that out. The outcomes in this sample space are numbers from 0000 to 9999. So that would be 10,000. So that's why we have 10,000 equally likely outcomes in the denominator. That's our sample space. There are 10 outcomes in the event. So the event that all four, now this once again is called the event. The event that all 4 digits are the same, well, you kind of have to, it sounds like it's going to be hard to find, how many there are out of 10,000. But if you start just kind of thinking through it, right? 0, 0, 0, those are all the same. 1, 1, 1, 1, okay. 2, 2, 2, 2, all the way up to 9, 9, 9, 9. And so there's from 1, 1, 1, 1 to 9, 9, 9, 9, that's 9. And then you also include 0, 0, 0, 0. That's a total of 10. 10 different outcomes in your event. And if you take 10 divided by 10,000, we get 0.001, which is 1 1,000th. Okay. As I kind of was getting to, sampling is a probability experiment. Sampling is a probability experiment. And I was trying to kind of show that a little bit by, hey, look what variable they're using there for the denominator of our probability. That is the sample space, and even the word there is sample, right? Sample space n. And when we're looking at the number in our sample, right, n is the sample size. Whoops, not m. Went a little crazy on making the bumps there. N equals the sample size when we're talking about when you're running a sample or a survey. So sampling an individual from a population is a probability experiment. The population is the sample space, right? Total outcomes, and the members of the population are equally likely outcomes. Okay. Sampling as a probability experiment. So there are 10,000 families in a certain town categorized as follows. Looks like we have 4,753 homeowners, 1,478 condo owners, 912 renters of a house, 2,857 renters of an apartment. Upholsterers samples a single family from this population. So they're not exactly telling us the method of sampling, but they samples a single family from this population. What is the probability that the sampled family owns a house? Okay. Well, owning a house looks like there's 4,753, so that is the event, and that goes up in the numerator. And we put that over the total population. There are 10,000 families, so there's 10,000 possibilities in our sample space. And so when we divide that, we get the probability is 0.4753, about 47.5%. Okay. Part B. So what is the probability that the sampled family rents? Well, renting comes in the form of renting a house or renting an apartment. So we need to add those two numbers up. And so we take our 912 plus 2,857, and we get 3,769 renters. Remember, renters, people who rent, is our event. And then we divide that event by the total sample space, which was 10,000 families, right? 10,000 families in a certain town. And when we divide that, we get our answer, which is 0.3769. Of course, if you ever wanted to change a decimal to a percent, you move that decimal point 2 places to the right, 37.69%. Now it's out of 100%. Okay, when it's written like this, it's actually out of 1, right? Out of 1. And when it's written like this, it's out of 100. And that notation, you could even kind of see it, right? This notation right here, somebody got creative and put a 0 there and a 0 there and a little line. But somehow that's connected, right? That it's connected mathematically solidly, but I mean, I think that symbol's connected too. I'm not sure the history of that percent sign symbol, but it means per 100. Okay. All right. Anyways, unusual events. An unusual event is one that is not likely to happen. So if someone says that's unusual, well, it's kind of like, well, can we put a math number on that, or is it just we just say unusual? In other words, an event whose probability is small. There are no hard, fast rules. I don't like that when there's no hard, fast rules. There are no hard, fast rules to justify how small the probability needs to be before it's considered unusual. There is a rule of thumb, though. Let's see, I ran out of my good color. Okay, anyways. But there's a rule of thumb. A rule of thumb, and it's kind of the default. Any event whose probability is less than 5, is considered to be unusual. So that's the default we go to. When probability is less than 0.05 or 5%, we say that's unusual. Okay. All right. An example of that. In a college of 5,000 students, 150 are math majors. A student is selected at random and turns out to be a math major. Is this unusual? Well, let's see. The event of choosing a math major is 150, right? So there's my event out of a total of 5,000. So that's 0.03. This would be considered unusual based on this 5% rule of thumb. So you have 150 out of 5,000, so 150 math majors out of 5,000 students. So the chances of getting a math major is only 0.03. So if you do get a math major, when you randomly select it, we would say that's unusual because that is the chances of getting is below 0.05. Approximating probabilities, empirical method. The law of large numbers says that if we repeat a probability experiment a large number of times, then the proportion of times that the particular outcome occurs is likely to be close to the true probability. So another way to say that is if you have experimental probability and you run the experiment many, many times, right? The law of large numbers, you run it many times. Then we say that the experimental probability will get closer and closer and closer to the theoretic probability the higher the number of trials you go. So the law of large numbers. I'm having a hard time saying that. The empirical method consists of repeating an experiment a large number of times and using the proportion of times an outcome occurs to approximate the probability of the outcome. Let me say that again. The empirical method consists of, so what is the empirical method again? Empirical method consists of repeating an experiment a large number of times. Why are you going to do that? Because if you repeat the experiment a large number of times, we know that that's going to guarantee that the probability gets close to its theoretic probability. And using the proportion of times as an outcome, using the proportion of times an outcome occurs to approximate the probability of the outcome. So by doing the experiment many times, we can approximate that probability, and we know that the more you do the experiment, the better that approximation gets. And there's actually maybe even the birth of statistics comes from some story, and I can't remember it. I better not put a date, but statistics is a newer mathematics out there, one of the newer ones actually, compared to algebra, geometry, calculus, stuff like that. Especially algebra, geometry. Statistics is one of the newer. In fact, it has its own area in math departments. Usually it's statistics, and then mathematics is one side, statistics is another, even though they're both math. It's that much different. But anyhow, what happened was they had a big cow or a steer or a bull or something like that at a fair. This is so totally paraphrasing, and they had one of those guess the steer's size and win the steer or win a prize or something like that. And they had guesses that were all over the place on how heavy this animal was. And then I can't remember which mathematician it was, but the mathematician realized that when they found the average and looked at all the guesses and averaged them, the guesses throughout the day or the week or how long people were guessing the animal's size, turned out the guess was really close to the animal's size. And that kind of sparked the idea of the law of large numbers, and then started this whole thing of statistics, or at least was one of the early ideas of it. I think that's pretty cool. Okay, on that, let's go ahead and do our math problems here. And so let's get up here to our adaptive homework problem 5.1. So when you take a look at this, it says a class is choosing a president, a vice president, and a treasurer. There are 3 students running for president. That would be Linda, Maria, and Anne. There are 2 students running for vice president. That would be John and Bob. And then there are 2 students running for treasurer. That's Amanda and Jessica. So the thing about a tree diagram that I really like is it shows all possible outcomes. And it also shows all the different combinations that you can put these people, right? Shows all the different ways that we can have a president, a vice president, or treasurer. And all you have to do is follow the branches of this tree to see that. Like if I want to see what happens, look at the possibility. Well, we got oops, that's the wrong one. What if we had Linda as a president, Bob as a vice president, and Amanda as a treasurer? Well, you can see the path of that, right? So I love tree diagrams. The downfall of tree diagrams is that if the outcome, and let's get our language here. Outcome. Remember, outcome is sample space. So outcome is sample space, and remember this is all possible outcomes. If the outcomes are large, and often outcomes of many things are large, this tree diagram grows so big and fast that you can't even really represent it on probably even like a poster board or sheet of paper. It's just too many, and it just gets so hard to draw. Becomes unusable really because of that. But it's really good for illustrating, things like this that aren't, the outcomes are not, the sample space is not too large, and it kind of gives you insight on this. Anyhow, let's go ahead and do this. A, how many outcomes are there? Well, with the tree diagram, all you have to do is just count them up, right? Let's count them up. How many outcomes? Well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we have a total of 12 outcomes. Part B, how many outcomes have both John and Jessica being chosen? Both John and Jessica. Well, that could be kind of confusing, but when you've got this right in front of your face, we're looking for John. They have to have both, though, not just one or the other. It has to have both John and Jessica being chosen. Well, it makes it pretty easy because I can see, well, John's here. So we've got John being chosen. So those are the ones John being chosen. And then it breaks down a little bit further to, dang it, what to say, John and Jessica. Okay, so then we break it down to Jessica. So you can see the path. Could be Linda, John, Jessica. Could be Maria, John, Jessica. But it makes it really easy to point out, or and John, Jessica. Makes it really easy to point out. And so you can see we've got 1, 2, and 3 different ways of getting that executive board. So how many outcomes have both John and Jessica being chosen? Well, that's just 3. Okay, and then finally, how many outcomes do not have Linda being chosen? How many do not have Linda being chosen? Let's do that in green. So I'm going to do this in 2 different ways just to show something. We're looking for ways that do not have Linda being chosen. So that means we do not want Linda to be chosen. So it's going to have to be the ones that have Maria and Anne, and kind of go from there. So you're going to see it's going to be these guys right here. 1, 2, 3, 4, 5, 6, 7, 8. Right? So you could do it that way. 8 outcomes do not have Linda being chosen. Now there's another way of doing this, and this is really useful when your sample space is super large, and it's easier to count the opposite of what you're looking for, and it's called the complement. But let's look at that. So if someone said, how many occurrences do not have Linda being chosen? What you could do is, if it's easier to choose how many have Linda, if it's easier to choose how many has Linda, then Linda. So how many actually have Linda being chosen? Looks like 4. So we can also answer this question by saying 1 is the total. I'm sorry, this is not a percent. You'd have to do the total sample space, which is 12, minus 4, which also gives us 8. So it kind of starts to give us this idea of these complements, right? If you want not Linda, you could actually say the total minus Linda. All right, let's see. A bag has 6 balls labeled A, B, C, D, E, and F. 1 ball will randomly be picked, and its letter will be recorded as the outcome. Give the sample space describing all possible outcomes. Then give all of the outcomes for the event of choosing a letter from D to F. If there is more than one element in the set, separate them with commas. Okay, so what we're trying to do is we're trying to show sample space and things like that. I think the actual answers to this, I can't remember how when you're doing this on ALEKS, they have the the cursor to tell you where to put things. But it says, well, let's just do this. It says, give the sample space describing all possible outcomes. Well, all possible outcomes on this would be, on there would be, you can get an A, a B, a C, a D, an E, and an F. That's the actual sample space. Then give the outcomes for the event of choosing a letter from D to F. Well, that's just going to be D, E, F. Okay. So sample space for the event of choosing a letter D to F. Okay, here's the answer. That's kind of a lame one. Anyways, D, E, F. It's really more or less trying to get you to talk about sample spaces and events and things like that. Here's another one. A bag contains 10 marbles, shown below. 2 marbles are yellow, 4 are red, 4 are blue. A marble is chosen from the bag at random. What is the probability that it's yellow? Write your answer as a fraction or a whole number. This part of the very beginnings of probability, they're leaving the fraction unreduced. We typically like to reduce them. I think the idea of leaving it unreduced, which is usually not something we like, but the reason why we have it unreduced, not reduced in this case, is trying to make that connection of the numbers, right? Because when it's not reduced, the bottom number is a sample space, and you could actually count, right, how many marbles, and that should match up with your denominator. Anyhow, we're looking for the probability that we get a yellow marble. And so the event is selecting a yellow marble, and I can see I have 2 of those. So I've got 2 yellow marbles out of the total sample space, which when I count it up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so there's the answer. Like I said, normally I'm a math person. I like that to be reduced, right? So anyhow, so that reduces down to 1/5. Okay. All right, so now let's take a look at the next question. A 12-sided die with sides labeled 1 through 12 will be rolled once. Each number is equally likely to be rolled, basically saying you don't have one of these not cheap, but these cheating loaded die, which means one side has more weight, so it rolls and lands on that side. What is the probability of rolling a number greater than 10? So what's the probability of rolling a number? What's greater than 10? Well, that's going to be, what's probably rolling 11 or rolling a 12? Well, the event of rolling 11 or 12, there's 2 possibilities. And what's the total sample space? There's a total possible 12 different numbers that you can roll on 12-sided die. And so that's the answer, 2 out of 12. Now, of course, talk to the math people, we do like to reduce that down to 1/6. If Alex is on this particular first 5.1 adaptive side is wanting to keep it as 2/12 not reduced, then just go ahead and do it that way. But for the most part, you're going to be reducing in the future. Number 5, a drawer is filled with 9 black shirts, 6 white shirts, and 5 gray shirts. 1 shirt is chosen at random from the drawer. Find the probability that it is not a white shirt. Write your answer as a fraction. So we want probability of not a white shirt. Not white. So not white would be, well, not white would be a black shirt or a gray shirt. How many black and gray shirts do we have? Looks like we have 14. And what's our sample space? Total amount of shirts would be 9 plus 6 plus 5, which is 20. And there it is. And once again, reducing that would be what? 14 divided by 2 is 7. 20 divided by 2 is 10. Number 6, a wheel has 8 equally sized slices numbered from 1 to 8. Some are gray and some are white. The slices numbered 2, 3, 4, 5, and 7 are gray, and slices numbered 1, 6, and 8 are white. The wheel is spun and stops on a slice at random. Let X be the event that the wheel stops on a white slice. What's P of X? Be the probability of X. Okay, so I'm going to use some color here. And I come up here, and they're telling us event x, and they want the probability of event p of x. So let's make sure we know what event x is. Let x be the event that the wheel stops on a white slice. There's event x. And they got this nice little distribution chart here to help us see this. What's the white? You can see on the spinner, we got 1, 6, and 8. So this helps us kind of realize that it's event of stopping on a white. We got 1 there, we got a 6, and we got an 8. So the probability of stopping on a white is going to be 3 out of a total of 8. Okay. All right, and then they've got another probability. It says, oh, here it is. So it says, let not x be the event that the wheel stops on a slice that is not white. So something that is not white is going to be this gray color. And I've noticed now that that this is an error. They've got an error right here. No, I better point it out. It's supposed to just say, it's just supposed to say p of not x. And so this 1 here is not supposed to be here. This little 1, they have a typo. So let me just get rid of that. I know when I saw that I was a little confused, and then I looked at the answers like, oh, yeah, they made a mistake. Let me get rid of that. Hopefully I don't, okay. So now what they want us to fill in here is what's the probability of not x? Well, not x, I'll go ahead and do it in green, is 1, 2, 3, 4, 5. So we have 5 not x's out of 8. Now down here, this is where they made their typo. Now down here, let me expand this out a little bit so I have a little space to operate. They want us to figure out what's 1 minus this green p of not x. Well, we know that p of not x, we just figured that out. That's just 5/8. So 1 minus 5/8. If you're not great with fractions, right, you have to have a least common denominator. And so that would be 8 out of 8. Isn't that the same as 1, right? So 8 out of 8 minus 5/8 leaves us with 8 minus 5 is 3/8. Well, that sounds familiar. So now they're going to try to get you to see why that sounds familiar. And here's the statement. Select the answer that makes the most, or makes the statement true. If I take, let me highlight this. If I take 1 minus, and then more important, maybe I should just, let me get rid of that. If I take 1 minus p of not x, guess what it's the same as? It's the same as just taking p of x. So p of not x and p of x are complements of each other, and they will add up to 1. So if you take 1 minus p of not x, then that'll be equal to p of x. All right, the spinner below shows 10 equally sized slices and spun the dial with 1,000 times and got the following results. So now notice this is an experiment. So that means it's going to be experimental probability. This thing is wobbly. I'm trying to hold it down. Anyways, so if you use these numbers, it's going to be experimental probability because these numbers came from an experiment. If you try to find the probability taking a look at this spinner, right, that's going to be theoretic probability. Whoops. Okay, so let's see. Let's see what these questions are. It says, fill in the table below. What table? Fill in the table below. Okay. That's a different problem. Maybe that shows up on the computer part. It didn't print out. So let me just do A, and we'll answer the questions. From Ann's results, so that's the experiment, compute the experimental probability. There it is right there. From Ann's results, compute the experimental probability. Experimental probability, of course, is going to be from the experiment. On landing on white. So on landing on white. So this experimental probability is going to be, well, how many times did they land on white in the experiment? Well, that was 405 times. Out of a total of how many times they spin in the experiment. When you add up all of the spins, we end up getting 1,000. In fact, they told us that they spun the dial 1,000 times. So this is out of 1,000. So when we divide that, we get a decimal, which is 0.405. It's about 40.5% is the experimental probability of landing on white. So assuming that the spinner is fair, compute the theoretic probability of landing on white. So the theoretic probability, that just comes from looking at the model, right? Whoops, look at the model. And the model has how many whites? How many white slices are there? It's 1, 2, 3, 4. So the model has 4 slices out of how many total slices? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 4 out of 10. That's the theoretic probability. And 4 out of 10 is 0.4. And if we want to have the same number of digits or places, it's 0.400, but it's the same as just 0.4, right? 40% or 4/10. And then finally, on part C, it says, assuming that the spinner is fair, choose the statement below that is true. Okay, let's see. It says the smaller the number of spins, the greater the likelihood that the experimental probability would be close to the theory. No, that's not right. Not the smaller, that doesn't work. Okay, so we crossed that one out. The experimental probability will never be very close to the theoretic probability, no matter the number of spins. Oh, that doesn't sound, that's definitely not right. The large, okay, here's the right answer. Let me underline or highlight. The large number, come on. It says the large number of spins, the greater the likelihood that the experimental probability will be close to the theoretic probability. So it's the law of large numbers is going to make the experimental probability get closer and closer to the theoretic probability, what we expect it to be. So the answer on this guy is that one. And finally, problem 8 out of 8, it says a coin is tossed 3 times. An outcome is represented by a string of the sort HTT, which means heads on the first and tail tail. The 8 outcomes are listed in the table below. Note that each outcome has the same probability. Okay, each particular outcome. But now we want an event. So what is this first event? This first event is looking for, I think I'm going to use color to try to see this. It says event A wants a tail on the last toss or the second toss, or both. So last or second or both. Well, that covered our bases there for sure. The last or second, no. Right, we want a tail. Tail on the last or second. A tail on the last or second, no. A tail on the last, yes. Last or second. A tail on the last, no, but on the second, yes. A tail on the last or second or both, yes, on both. A tail on the last or second, it's on the second. Tail on the last, it's on the last. So when I look at that and count it up, what is the probability that event A happens, which is a tail on the last toss or the second toss or both? That's going to be how many? 1, 2, 3, 4, 5, 6. That is 6 out of 8. And that reduces down to 3/4. Now they want to reduce it, huh? That's kind of frustrating, in my opinion. But I think it was really, they did that for trying to see the numbers. But I think they should be consistent till the end of this page at least. Now part B is exactly one head. Exactly one. So that's not the case here. That's not the case there. That's 3. That's 2. There's exactly one head. There's exactly one head. There's 2 heads. And there's exactly one head. So that's going to be 3 out of 8, which doesn't reduce. And finally, my last trick in red is going to be event C is 2 or more tails. 2 or more tails. Okay, well that doesn't have any, I'm sorry, 2 or more tails. Yeah, that has 3 tails. That's really covering ourselves. That's 1 tail, so that doesn't work. That's all heads, no tails. 2 or more, that's 1 tail. But now I see a tail, so that works. I see a tail, so that works, right? 2 or more tails. I see 1 tail, so that does not work. I see a tail, so that works. So it looks like we have 1, 2, 3, 4. That's 4 out of 8, which of course reduces down to half. All right, and I think that is it for us. Yep, the rest of them were notes I did before. I hope that helps out, and I hope everybody's doing great. This is on the adaptive side. I'll go ahead and do some for the assignment side. I don't think there's a 5.1 on the assignment side, but there is a 5.2 on both sides, so we'll get that going. Okay, I hope you guys are having a good day and a good weekend coming up. Take care.